Well, I guess we can get started. Welcome everyone to the AstroAI lunch talk. There won't be a talk next Monday because it's a holiday, but today I'm very pleased to introduce Helen Shao. Helen started her PhD here at Harvard with Daniel Einstein, and today she will present us the work she did as a master's thesis at the University of Cambridge, working together with Fiona, Kathy, Miles, Cramner, and Blake Sherwood. And she will be telling us about the polarized CMB, which is very important for testing inflationary theories, and in particular, how to separate the signal from the actual primordial CMB from any foreground emission using diffusion models and convolutional neural networks. So, and how that compares to baseline models. So, Helen, thank you very much for doing this in a short notice, and the floor is yours. I encourage you guys to interact with questions anytime during the talk. This is interactive, and other than that, the floor is yours.
Thank you. Yeah, thank you. Thank you for the introduction and for having me here today. I'll be telling you about how we can use machine learning to better detect a very important signal all the way from the early universe, known as the cosmic microwave background, by carefully removing this excess astrophysical foregrounds that are in our way, while making sure that we don't accidentally distort that original signal of interest. And it's called signal preserving CMB reconstruction. So as Raphael mentioned earlier, why do we care about the CMB? Well, among its many uses, the CMB can tell us what happened in the universe is within the first second after the Big Bang, during which our inflationary models predict the existence of primordial gravitational waves, which will induce a unique imprint on the polarization field of the CMB. And this polarization looks something like this. Now we are on the lookout for curly patterns in this polarization field, referred to as primordial beam modes. The reason why is because such beam modes would only be created using tensor perturbations produced by inflation. So many upcoming experiments and surveys are trying to detect the signal in hopes of testing different models of inflation. Now, this is the pipeline, but there's a major challenge in this procedure, namely at this step, when we actually try to go out and measure these primordial beam modes if they exist. And I'll mention two of these challenges today. First, primordial beam modes are inherently tiny, which you can see from this plot of power spectrum, showing you the signals that we can get from the different components of the CMB, temperature, E mode, beam polarization. The beam polarization shown in red are orders of magnitude smaller compared to the other signals, especially on large scales, where we can actually distinguish between the effects of various inflation models. And what's worse is that the beam polarization is also heavily screened by foregrounds that are in our way. So when we observe the CMB, we can't really access this clean, pristine primordial signal. The photons are screened by a bunch of astrophysical foregrounds, most of it coming from our own galaxy, ranging from polarized dust emission to synchrotron radiation. So what we actually observe inside of this map is a heavily contaminated, very noisy observation. So with these problems, you might ask, well, how do we even detect a signal of beam modes in the first place? Well, this motivates the need for foreground removal methods, and not just any foreground removal method. We want a method that gets rid of the astrophysical noise, basically, without biasing or reducing or taking away any information that we hear about from the early universe. And it's called signal preserving foreground. So I'll just give you a quick outline of what we're talking about going forward. I'll introduce you to the traditional method for doing this called internal linear combination. It's been used over and over again, it's really robust, and it has the signal preserving property that we hear about. But then I'll argue that its limitations drives the need for non-Gaussian methods, non-linear methods, such as neural networks, to improve upon the signal reconstruction. And we'll be using neural networks to look at two different types of information that we can get to do our foreground removal from frequency correlations as well as scale correlations. And then I'll show you the results that we get from both methods. So just to give you an understanding of how the traditional linear method works, it does so by looking at frequency correlations between our different observations of the CMB. So we can observe the CMB in different wavebands and different frequency channels. And what's cool is that in certain frequency channels, or high frequencies, for instance, we might have more of one emission than other types. So for high frequencies, we might have more dust, and for lower frequencies, we might have less dust or more synchrotron radiation. And so this correlation, this relationship, you can see it in the SUVs here. And the fact that we have these correlations means that we can try to find an optimal balance between our different observations across frequency space to overall minimize the contribution from all of the astrophysical galactic emission. And this is what the ILC does. So to show explicitly, let's start off with the primary CMB. This primary CMB in blue is present and the same in all frequency channels. On top of that, we have our galactic foregrounds, which vary from ℓ1 to ℓ2 across the different bands. So combining them gives us our actual observation, this messy CMB, which varies across frequencies. So the internal linear combination method basically takes these different patches, these different observations across bands, and finds a series of weights, such that once you add them together in this linear combination, you get a recovery of the primary CMB. This is called the ILC reconstruction, or ILC solution. And this is a simple linear optimization problem that you can solve for under the constraint that these weights that you use here sum to unity. And one can show that under these conditions, the weights can simply be given by the covariance matrix in your frequency space. But what's key is that we have this constraint that the weights sum to 1, because this is what ensures that the ILC fully preserves the primary CMB. And I'll show you explicitly here. If you take a look at what the weights are doing in the sum, you can basically decompose it into your primary CMB and your astrophysical foregrounds, which nicely divides into 2 parts. But because the weights here sum to 1, you can, in the first part, we'll basically have our entire fully recovered CMB. And in the second part would just be any residuals that the ILC was unable to remove, any remaining excess foregrounds. And we'll call that delta ILC. So this is the structure of the ILC solution. But while it's robust and signal preserving, there are some key drawbacks that we want to investigate further. One, it is limited by the number of frequency bands we can observe in. And because it's finite and this method is inherently suboptimal. Second, it discards higher order correlation. So I mentioned earlier that these weights can be calculated using just the covariance matrix of your CMB observations in different frequency bands. So by construction, the solution is not taking advantage of all the additional non-Gaussian information that we know to exist in our foregrounds, because it's described by highly nonlinear physics. So in the end, our problem reduces to this: how can we find a mapping between our messy observations and the pristine primordial CMB that we want to recover? And the reason why this mapping is so tricky is because while the primary CMB is a Gaussian field, can be described entirely by 2-point statistics, the same cannot be said for the highly non-Gaussian foregrounds. So whatever this mapping that we're trying to learn cannot be captured entirely by the ILC solution. Alternatively, maybe we can use a neural network to extract the additional non-Gaussianities in this relationship. And we can do this for simulations where we both know we have access to the foregrounds and the primary CMB. But then the critical issue is, how can we make sure whatever the neural network is doing is also signal preserving? We want it to be reliable, like the ILC. We want to make sure that whatever foreground removal or cleaning it's doing, it's not messing up our primary signal of interest. And this is a key issue because if we're using simulations, we have model specification, we have biases from our simulations. So we don't want to run into issue where we're accidentally subtracting part of our primary CMB or introducing some bias that shouldn't be there. So we want to construct a network that respects the signal preserving property of the ILC. And how do you do this? Well, let's recall the structure of the ILC solution. It divides into two parts, a signal only part and the part of the residuals containing anything uncorrelated with a primary CMB. Now, this part is what we want the neural network to fulfill, meaning that as long as we don't feed the network anything correlated to the primary CMB, it won't output anything that can bias the signal that we care about. So let's think of how we can design a network that can respect this characteristic. Well, we first considered a pipeline using different frequencies that Fiona McCarthy introduced. And I'll walk you through the design of this network, but it does get a little confusing, so feel free to interrupt me along the way. So we'll start off with our primary CMB that we want to recover. That's the signal we care about. But we don't have access to it directly because what we actually measure are these messy observations at different frequency channels. But what we can do is, well, initially as a pre-processing step, feed these different frequency channel observations into our ILC algorithm and get a linear reconstruction solution. So that's in purple. But then we take this linear approximation and remove it, subtract it from our initial observed maps in green. And because the ILC solution fully contains the CMB and the observations fully contain the CMB, the difference is signal free. It doesn't contain the CMB and only contains the residual foregrounds that the ILC was predicting. Now these we can feed the network. It's signal free input. And we're going to ask the network to then predict what is the residuals of the ILC solution. What was the ILC unable to pick out? And then once we have a prediction of this residuals, then we can subtract it from our ILC solution and essentially get an improvement on the ILC reconstruction. And this again uses the fact that we have correlations among our frequency bands to do the reconstruction. So this is like our first method, and just as a side, we're using convolutional neural networks for this in a very basic vanilla unit architecture, just because we wanted something that can respect the dimensions of our CMB observations and use multi-scale feature extraction. So just as a very simple test, we just want to first make sure that the neural network predictions is giving us something that is an improvement upon the ILC. So just doing simple mean square error comparison, and we want the neural network corrected CMB reconstruction to have a lower error, so we want points to fall below this y equals x line to indicate that the ILC solution has a larger error. And this is indeed what we see for majority of our test data sets. You can also do this comparison at the level of the power spectrum. So here I'm showing you the power spectrum of the in vivo polarization. In orange, we have the auto spectrum of the primary B modes. And we're going to compare the red and the blue. The blue is the neural network corrected reconstruction, and the red is the traditional ILC method. And again, you can see, as expected, now both of them give you much higher variance at lower scales because we have additional variance or noise coming from the astrophysics. So this is behavior expected, and we do want to see a reduction in the variance when we use our neural network improvement. And there is a slight improvement here, and I'll go more into this later on. But what's key is that when we cross-correlate the neural network reconstruction with the primary CMB B modes, that we fully recover the auto spectrum or the orange line, showing that indeed the neural network reconstruction fully maintains the primary CMB, and we're not removing part of that primary signal. Okay, so that was our first approach using this multi-frequency correlation. But how can we do better? Well, another set of correlations that we can consider.
Sorry, can you go back a couple slides to the diagram where you had before this one? So basically, do I understand correctly that what you want your neural network to learn is any residuals that result from the non-Gaussian of the dust emission? Is that what you're trying the neural network to learn? In what sense is this first subtraction between your ILC solution and the data signal free? Can you just
here it is.
go again over
Yeah.
that?
Yeah, good question.
Yeah.
A little confusing. Yeah, so the ILC solution that we get contains fully the primary CMB model by design because it's signal preserving. We also have the fully primary CMB in our observations, in our observed maps. So we subtract them to get rid of the primary CMB component. And so this information that's left over is kind of like the ILC estimation of the foreground informational. But because it doesn't contain the primary CMB, we can safely feed it to the network. So the network wouldn't be biased to any model of the primary CMB on our simulations. And that's what we don't want.
So does the ILC assume that the primary CMB and the foregrounds are, or like the CMB and the foregrounds are completely uncorrelated?
ILC, yes. Yes.
And like, do you have a sense of how true that statement is? Like, because I'm imagining if you have like a hotspot on the CMB, then there's probably that evolves into like some galaxy cluster in front of it. So
Yeah, that's a good question. I think for galactic foregrounds that we're considering, there's no correlation. Maybe like we're looking at extragalactic astrophysical sources like SZFX, maybe you can trace some signal from a primary CMB to the intermediate redshift range. But for a galaxy, for Milky Way emission, we don't think there's any correlation between that and the early universe.
For beam mode going for the
and like just to follow up as well, like so are you considering like the lens B modes here?
Yeah, that's a good question. Yeah, for this we haven't looked at B modes created by lensing, but that is something I want to talk about. Yeah, thank you.
More questions, comments? Even from non-cosmology experts? Yes?
Yeah, so you're basically giving the network what the ILC thinks the foreground looks like.
Exactly.
And I guess having it predict what it missed or whatever.
Exactly.
But what information is it going off of? Like, it's kind of just taking a guess.
Yeah, it's using the correlations between the different frequency channels. Because you can get an estimate of how much foregrounds to remove if you know across the frequency bands in which band there's more of one frequency, more of one emission versus another. So there are some like trade-off relationships that can use to try to find out. Yeah, but that's for the multi-frequency case. Things will change when we look at scale correlations. Yeah, okay. So yeah, that earlier method I've shown you was taking advantage of the fact that we have multi-frequency correlations. But we were wondering, okay, what additional information can we learn from in our observed B-mode maps? And we took a look at interscale correlations. So we know that for the primary CMB, because it's a complete Gaussian field with some caveats, the large scales and the small scales are independent. But the same cannot be said for the observations because they contain galactic foregrounds and the complicated physics, a couple of different scales. So you can see this visually in patches for CMB, where information from small scales gets traced over and leaves an imprint on the information in the large scales. And this is great news because it means in principle we can take small scale patches, small scale information, and use that to learn something about our large scales. And as mentioned earlier, because we really only care about the large scales for distinguishing between different inflation models, we can feed a network small scale information, primary plus foregrounds, all of it, without it being correlated with our primary CMB large scales. So this information is still signal free, and we can use, the scale dependence here. And we can do this analysis now with just a single frequency channel. So it's great because we can collapse this messy pipeline into a much more simpler procedure. Again, starting with our observations, but just at one frequency channel this time. And doing a filter, so basically just taking our small scale information, only containing both the primary and the foregrounds, and we can safely feed it to a network. And this time ask the network to predict the large scale foregrounds, because the foregrounds on different scales are correlated. And once we have a prediction of the large scale foregrounds, we can remove it from our observations and get a reconstruction of the large scale primary CMB, which we care about for inflation. And because the large scale CMB, the primary CMB, the small scale primary CMB are independent across different scales, this process is still signal free or signal preserving, and the primary CMB can propagate through this messy algorithm and be maintained or preserved. Okay, so to do this in practice, we're using simulations, full sky simulations coming from the dust filament models developed by Hoffenberger. And basically, here we're just looking at galactic emission from dust filaments in the Milky Way. They model millions of these filaments in alignment with our galactic field magnetic plane. And for the neural network data set, we're taking patches of this full sky, separating them into small scale and large scale inputs. So the inputs would be small scales, and then want to map it to our target inputs to the small scales and map it to large scales. And again, you can see just by eye that there's some correlations. There's a relationship between the signals we get at the larger scales compared to the inputs in the small scales. Okay, so let's see what the results look like. On the left column, I'll be showing you the true large scale foregrounds that we want the network to predict. And then on the right, I'll be showing you what the network prediction looks like. And again, this is learning just information from the small scale foregrounds. So here are some of these patches, and you can just see by eye already the network is able to do a pretty good job in recovering the large scale B modes with low mean squared error and pretty high correlations. But let's quantify this performance. So it's taking a pair of patches in our test set and seeing first how correlated is the network prediction and the true foregrounds in harmonic space. So taking a cross correlation, and this is what we get. We have these the string line here showing you the cross correlation between these two patches. And again, it's by itself very high, but we want to compare it to the distribution of possible random correlations that we can get with this patch. So this is shown in this yellow region here, which I computed for basically by cross-correlating the network output with every other region in the sky, which we expect to just have random correlations, and showing that the green curve stands out above this distribution. So we're not seeing like a random correlation, it's actually a positive signal. The blue curve is just the mean cross correlation between every pair of patches in the data set. So this is harmonic space. We can do this similarly in pixel space, just doing computing a scalar correlation coefficient. It's hard to see here. Yeah.
Sorry, is there any information in the fact that the random correlation between patches happens more at particular spatial scales? You know, the fact that the shape of this is like larger at small L. Is that telling you anything about?
That's a good question. Yeah, I mean, I guess if you're looking at scales that's spanning the entire sky, I'm guessing maybe information from one half of the dipole moment might tell something like the other half of the sky. But yeah, we haven't looked into it for the full scale. That's a good question. Yeah. Yeah, although for this analysis, we are removing the galactic plane just because we don't realistically expect to detect B modes in that region. It's way too messy. So I'll have to look into where the extra correlations are coming from. But yeah, good question. And yeah, we can do this in real space, just computing the scalar correlation coefficient, which is shown by this green line here. And again, it stands out above the distribution of possible random correlations that can exist. Yes, okay. And then we can also go to ensure that we have the classic mean square error comparison. We want the neural network reconstruction to have lower error than the ILC solution. And this is indeed the case for over 90% of our test pouches. Is good news. And this is preliminary results, but there has been in the past, Oliver Philcox has developed an analytic method similar to this, where he looked at predicting the one large scale in the CMB beam modes, the hexadecimal, using the fact that it's has angular dependence to see analytically how we can predict large scale beam modes from other scale information. And here I'm just comparing my results to his. So he predicted foregrounds that had a correlation of around 0.5. The simmers were higher, for larger L or smaller scales. And I'm showing you how my results in the red curve compares to his correlation. This is, still very preliminary, and we have to do some more tests, but at least we have an analytic baseline for how well theoretically this method should work. But also, like, I know it seems like he has really low correlations, but his method only looks at one particular mode, one particular mode in ECNB. Okay, so just to wrap up, we started off with our traditional internal linear combination method that has this really neat property that's signal preserving, but unfortunately it relies on multi-frequency bands and it only is able to extract Gaussian information. We extend upon this using non-Gaussian information coming from our foregrounds and leveraging that information with neural networks, so we could take a look at interscale correlations while making sure that this our method maintains the signal preserving property that we care about. And we can do it using just one frequency band, without having to access multiple channels. I can leave you off with some of the ongoing work that we're still investigating, including what happens if we use or leverage additional independent signal-free pieces of information, like the emo polarization, L scales, or temperature maps. These are independent measurements of the CMB that can, in principle, inform us about our emo polarization. So I'm still trying to see how well this will work. But again, you can see by eye, the same physics that show up in these different maps can inform us about the large scale beam modes. So we'll see if that works. So far everything I've been talking about has been just using convolutional neural networks, giving us point estimates of the maps. But it would be nice if we can get not just a mean square point estimate, but a distribution of what the foregrounds look like. And for this, we would need diffusion models or generative AI. And just as a debrief of how it works, diffusion models basically randomly add noise to the signal that we want to recover, and then iteratively remove that noise. So by iteratively removing that noise to learn the underlying distribution of the signal we care about, because we're doing like a mapping from the Gaussian probability distribution to an unknown distribution. And condition on the fact that we know stuff about the small scale. So it's a condition probability distribution that we're trying to learn. I'm still trying to figure this out, to be honest. It's been a couple of months and I still haven't been able to get the diffusion models to converge. So if any of you guys have any tips or tricks for diffusion models, feel free to let me know. And this other future steps in the long term, make sure that the method algorithm is robust across different simulations or different dust models. Maybe use a hybrid interscale and interfrequency correlation method. And then later on, yes, we do need to consider the fact that our CMB beam modes can be generated by lensing of E modes. But I think with this problem, we can separately consider the delensing map as a different channel. But I'll have to look more into that. And then also there's some systematics that we should take into account for realistic experiments. And then in the very long term, how to translate all of this improvement into cosmological constraint of inflation parameters. So yeah, a lot of stuff that I still need to look into, but stay tuned and thank you for your time.
Thank you, Helen. Okay, questions, comments? Bill?
Yes, so thinking about additional information like your last one and really conditioning your model. Have you thought about, like, we're generating very detailed dust maps now of the Milky Way from things like Gaia, and they're probabilistic and they're. Have you ever thought about conditioning one of these models on one of these dust models that we're generating?
Oh, yeah, I'm not aware of any of these models, so maybe if you can let me know where I can access that data, that'd be super useful. But yeah, definitely, if we have access to other simulations, and it would be great, because I think for a long time in this project, I was limited to the simulations and the data products I have access to. So yeah, it would be great to see how well, or what other information we can get from other Gaia-based models. Thank you.
Thanks.
Yeah.
So we know that there are different dust populations in various areas of the galaxy. You said you mentioned mass in the galactic plane. But do you know that whether there be any bias from training over most of the sky beyond the plane, and whether those populations could be different at the very clean patches and use that each significant measurement?
I see. So like you're asking if we can learn something about different dust models from information on galactic.
Well, I was saying, have you looked at, say, training on, parts of the sky that are, mid latitudes, but then try to use that to clean the high latitudes where, and seeing whether that introduces bias?
Yeah, yes, that's a very good question. Yes, we have tried doing that, and actually, what we found is that using information from the galactic plane actually worsens our model predictions, maybe because the models of the dust filaments in those latitude ranges significantly biases the whatever the network is learning. So in the end, we just decided to exclude that region. And it was, we saw it consistently across different dust models. So unfortunately, it wasn't really helping us. But I do know that, like for ILC methods, there are some variants of the ILC that look at different spatial parts of the sky and correlating them.
Okay. More comments, questions? So you early on in your talk, you mentioned model specification, and I would think, without really being an expert in dust, that dust is one of those things that is really hard to model. So regardless of what model you end up using for the dust, have you thought of incorporating any strategies for mitigation of any model specification on your approach? In other words, how do you plan to deal with that?
Yeah, exactly. How to make it robust, different simulations. I have started to using transfer learning to get predictions based off of data from one set of simulations, and then fine tune these weights to another set of simulations. I still need to check on the results for that, but it is very important and very difficult because it's a domain adaptation problem. We don't really know which models are more correct, and they all have their different way of modeling the behavior of dust. So it is definitely a tricky problem that to look into.
Good. Okay. Looks like you're interested in talking about diffusion models, so I know you attend the Thursdays meetings, but that's a good space to bring these questions up, get some suggestions from them. So, all right, I guess everyone is leaving this room being an expert on B modes and machine learning. So I guess that's a good outcome. They don't have any more questions. So thank you very much. Let's thank Helen. Thank you.